it is expected to deposit a very thin quality silver plating on an iron ring using the following setup. Which of the following statement true? Here we have the iron ring. This is the iron ring. Fp. And solution B is the silver. We are supposed to apply this Ag on this. Normally, the Ag, the solution A must contain Ag plus. Right? It's better if you can use Ag cyanide. Why cyanide is important? We need the very small concentration. If the concentration is very small, then the process is much slower. If the process is slow, it can take enough time to form the real silver crystal or real silver crystal structure. If the crystal structure is strong, then only the plating is good. Otherwise, it will peel off, or sometimes it will remove from the surface, the plated surface. So, why this is important? Normally, AgCN, or sometimes you can get that Ag is, say, ammonia complex, because in this question it says something about this complex. Ag ammonia complex is very stable, so it gives very small amount of Ag plus Aq to the medium. Because that the Kc is very small, then you will get 2 ammonia Aq. Then because of that reason, the Ag concentration is very small. So if the electroplating process is slow, then only we can get a better coating. Otherwise, that coat may be removed from the surface in short period. So this must be Ag. Then the solution may be Ag cyanide or Ag amine complex, like this. It is plus, silver is positive, plus 19. Okay. Now we'll go to the ring should be connected to the positive terminal of the supply cell. Now we have Ag ions in the solution, and we have to give electron and reduce that to Ag and deposit on the surface. Deposit on the ring. So it has to be reduced. To be reduced, there must be electron. So electron will be available in this case on the negative terminal of the external source. Here reduction is taking place. It must be connected to the negative terminal, and the Ag rod has to be connected to the positive terminal. Then what happens at the positive terminal? Oxidation will take place. Ag plus plus electron. We need to remember that in electrochemical cell, the anode is a negative terminal where the oxidation is taking place, and cathode is the positive terminal where the reduction takes place. But in electroplating or electrolysis, anode cathode will be changed. Actually, the chemical processes remains unchanged. That means wherever the oxidation is taking place, that is the anode. Wherever the reduction takes place, it is the cathode, but positive negative terminal will change. So the negative terminal of the external power source must connect to the electrode which we need to be plated. The ring should be connected to the positive terminal, that is wrong. If you connect that to positive terminal, you don't get the coating. Second one, Ag cyanide complex or Ag amine complex has to be used. Solution is more suitable than the AgNO3 solution for A. Yeah, that's correct. What's wrong if we use this AgNO3? Nothing wrong. Ag will be deposited, but that Ag depositing much faster than the plated process taking place when we use this Ag amine complex. Therefore, the coating may not be strong, that coating may not be shiny, and there are many things behind that. So normally we don't use just Ag plus ion. The ratio of the current used to the surface area of the ring should be small. Yes. Ratio is small means we are giving electron very slowly, then Ag will deposit very slowly. So in order to ensure the electroplating process is slow, we can use a very small charge density. In this case, it will take little time to complete the plating process, but still we can obtain a better quality. So that is correct. Next one, 9 should be used in the place of B. No, we have to have silver or deer. Otherwise, silver may be plated until the silver ions cease in the solution, but it's better if you can provide continuously silver ions to the medium, then it will continue the plating process because we have enough Ag plus ion conservation. Here, this is the reaction Ag plus electron. So, B must be silver rod or silver metal. So, BC correct. The answer is 2. Ca3NH2 react to Ca3MgCl. Yes, this is methylamine. Methylamine is a primary amine. So this is Grignard reagent. There are something which can provide H plus to the Grignard reagent, like ammonia. Ammonia can give hydrogen to this. Say X. Ammonia. The other one is primary or secondary amine. Water. Any acid is strong or weak. Compound having terminal hydrogen means any alkyne having terminal hydrogen. Alcohol, phenol, and anything which can provide H plus easily will react with that. So if I get this, for an example, we have the CH3MgCl. We add in that the CH3NH. Then the product will be CH4 plus CH4 because hydrogen will be given and the byproduct. It will be CH3NA NH2 like that. Okay, it reacts. That is correct. Second one can act as a base. Yeah, this can act as a base because it has a lone pair. But that is not the reason to react with this. Being a base is not the reason to react. Right? If you add H plus to this and acid, it will give us CH3NH3 plus. So acid base will react to give us this salt. Therefore, it can act as a base. That is correct, but there is no any relationship between these two statements. So therefore, both statements are correct, but not explain the first statement by the second. So answer is second one. Next one. CH3, CH2, Cl is formed. That is called chloroethane is formed when is reduced by lithium aluminum hydride. Normally remember that by reducing carboxylic acid, so their derivatives we can obtain alcohol. If it is an amide, you will get primary amine. So in this case, you will get Ca3, COCl. If you add lithium aluminum hydride, the product you get will be this one. So the next one, lithium aluminum hydride can be used to reduce carboxylic acid derivatives. Yes. Remember that carboxylic acid, though their derivatives cannot be reduced by using sodium borohydride, because sodium borohydride is not a very good or strong reducing agent. Is a good reducing agent which we can use in organic chemistry, but that's not a strong one. That means that is not strong enough to reduce. So this is correct and this is correct. It means the first statement is correct. Second statement is also correct. The first statement the is reduced by this is formed when this no. The product is wrong. can be reduced, but product is wrong. Therefore, the first statement is wrong. Second is correct. So answer must be the fourth. Incorrect, correct means fourth. Here, in the Solvay process of producing sodium carbonate, ammonia gas is passed through brines saturated with CO2. Yes. Here, in the production of sodium carbonate, first what we do, we have two towers like this, very tall towers. In the first tower, we allow concentrated sodium chloride, though we call that the brine solution, to fall from top to bottom. Then we pass ammonia from the bottom, and then we get the sodium chloride, which is saturated with ammonia, and then it will send to the second tower. In the second tower, we allow CO2 rise through the column or through the tower, and now we have the sodium chloride. Actually, it is now basic because this ammonia has been dissolved in that basic, and carbon dioxide is acidic. This is basic. CO2 is an acidic acid. Then, because of we are using that basic solution here, it will increase the amount which dissolves in this solution. The CO2 amount dissolves in solution. So here we first pass the ammonia, then pass the CO2. If you change that, no use. This must be the sequence. This must be the order. Then only we can increase the efficiency of dissolution of CO2 or CO2 in water. So gas is passed through the brine saturated with CO2 නෙවෙයි. එතකොට first statement is wrong. We pass CO2, gas pass through the brine saturated with ammonia. ඒවයි වෙට්ටු. Right. So the first statement is wrong. Second, the solubility of ammonia in an aqueous solution saturated with CO2 is greater than the solubility of ammonia in water than the temperature. That's true. Why? If you use basic medium to dissolve acidic gas, definitely the solubility will increase. So we use this order. So the second statement is correct. As a statement, it is correct. But that is not applicable to this Solvay process. So again, the answer is fourth one because first statement is wrong and the second is correct. CH2, CH2Br. This is an unsaturated halide or halide containing compound, organic compound. Shows a greater tendency to undergo single-step electrophilic substitution reaction. Remember that there are two such reactions related to the alkyl halide. This is unsaturated alkyl halide. If we just get that the saturated one, normally remember that the reaction will be fast. Reaction will be fast if the product you can obtain after the or as an intermediate is stable in this case. Here we can consider about the number of steps in this reaction. How you know? If the ion we obtain by removing this bromine is stable like this. CH2 double bond CH, CH2Br. Then this bond will be breaks. If it breaks, then you can consider CH2 plus. Sometimes you will get such. Plus Br minus. So in our case, this will be the intermediate. So if the intermediate is stable, then the reaction will be two-step. Otherwise, single step. Now, if you add, say, sodium hydroxide into that, now you have that OH minus will react with this, giving CH2 double bond CHN, CH2OH. So, this is the first step. This is the second step. So, second step, if a reaction is two-step, that means the intermediate carbocation is stable. Or in other words, if the intermediate carbocation is stable, then the reaction is two-step. What will happen if CH3, CH2, CH2, Br is used? In such case, again you can remove this Br and get this CH3, CH2, CH2 plus primary carbocation. This is also primary carbocation. Both of these are primary. Write it in short notation. Primary carbocation. Say cation, primary cation. But this is not stable as the above one. Therefore, this will not wish to form. It is not willing to form this kind of thing. Therefore, what happens? The OH minus and the formation of new bond and breaking of the old bond will take place at the same time. Therefore, the reaction may be single step. Why this is two-step and this is single step? In this case, the carbocation is stable. Why and how? Why it is stable? Or how it is stable? Here we have a pi bond. That pi bond will be broken into this side, giving negative charge to this and positive charge to this. Like this way. CH2 plus CH. Now we have lone pair and negative charge. Why? This bond will be broken into this side. Plus CH2 plus. In this case, this lone pair can form a bond with this carbon. So the double bond, sorry, now we have this lone pair and this one. So plus charge will be here and this will be a double bond because of this. Then double bond can be shift from one place to another place. So it has two resonance structures. If you can draw more and more resonance structures for a given iron or molecule, that will be stable. So this carbocation is stable than this primary carbocation. That's why this tends to go through two step, while this is definitely a single step. If the carbocation is a tertiary carbocation, normally we know that tertiary carbocations are stable. So such reactions are normally taking place in two steps. So primary carbocations always single step. Tertiary carbocation or tertiary alkyl halide undergo nucleophilic substitution reactions in two steps. So secondaries, we cannot say. The secondary depend on some factors. Condition of the medium, pH value, temperature, and many things has to be considered. Some other kinetic factors. And also thermodynamical factors has to be considered. So in this case, remember that shows a greater tendency to undergo single step. No, it has a greater tendency to go in two-step reaction. Therefore, the first statement is wrong. Second one is a primary alkyl halide. Yes, because the halide attack, the carbon with the halide attached has only one other carbon attached to that. Therefore, it is primary. So, incorrect, correct answer is again the fourth one. The solubility of an ionic compound in water depends on the hydration enthalpy and lattice enthalpy of its ion. The solubility of an ionic compound in water depends on the hydration enthalpy and lattice enthalpy of its ion. The solubility of an ionic compound in water depends on the hydration enthalpy and lattice enthalpy of that. Yes. The solubility. We get very common example which we are discussing in our syllabus is comparison of the solubility of this barium hydroxide and barium sulfate. Or this refers actually the hydroxide of group 2 and the sulfate of group 2. These two have two different solubilities. When we move from top to bottom of the second period, beryllium hydroxide, magnesium hydroxide, and barium hydroxide. We have some other things in between, calcium, strontium hydroxides. So here the solubility is increasing, but if you get that the beryllium sulfate, magnesium sulfate, calcium sulfate, strontium sulfate, and barium sulfate. Here when we move down, the solubility decrease. Solubility decreases. Here solubility increases. Why? It says that the reason behind that one is given as the reason. We have to consider two things. The one thing is the hydration enthalpy, say delta H, and the lattice enthalpy, say delta H, hydration and delta H. Down the group, hydration enthalpy is increasing, the lattice enthalpy is decreasing, therefore the net effect will be negative delta H change. That means it elaborates amount of heat during the dissolution process. Why we have to provide some amount of energy to break the lattice, and then the hydration process is taking place, and in that case it will release some amount of energy. So, but in the case of sulfate, the sulfate lattice is strong, therefore we have to provide, or down the group lattice become strong because the ionic is increasing. So the solubility will decrease. Why? The lattice enthalpy is increasing, hydration enthalpy is decreasing. Why hydration enthalpy anyway decrease down the group? Because the hydration enthalpy of the cation is decreasing because of the decreasing of the charge density of the central atom. Because of the decreasing of charge density, it is decreasing. So the solubility of sulfate decreases while the solubility of hydroxide increase. That means what I need to tell you is the solubility is solubility depend on the hydration enthalpy and the lattice enthalpy of some ionic compounds. So the solubility of ionic compound in water depends on that. Yes, that's true. I gave you that typical example because that is the only place where we discuss about that. As the standard lattice enthalpy is greater than the sum of the standard hydration enthalpies of the relevant ion, the standard enthalpy of the solution of an ionic compound in water is always exothermic, and the standard lattice enthalpy is greater than the sum of the standard hydration enthalpies of the relevant ion. The standard enthalpy of solution of an ionic compound in water is always exothermic. That is wrong. Eh? Why? That's what I explained here. The effect net value is not a exothermic all the time. We cannot assure that. So answer must be the